This is the lecture for Wednesday, September 19th. We are going to talk about projectile motion. So by a projectile, I mean a ball thrown into the air, a cannonball shot from a cannon, a football kicked from the ground, any sort of thing that's flying through the air. Okay, so I have the plus x direction, this will be horizontal. And then I have the plus y direction, which will be vertical. And we have something, let's say, maybe shot from a cannon. Here's level ground. And there's some initial velocity to the projectile. And it makes this parabolic trajectory, parabola, upside down parabola. The types of questions you might want to know are how high does it get? Notice how high does it get like this? Or how long is it in the air? So maybe delta t is the question. Or you might want to know how far does it go horizontally. That's what's called the range problem. So maybe we will call this, well, we'll just call it R for range. Okay, so we're going to think of an object traveling through air. We have an object traveling through air. We will neglect, unless we say we are considering it, we're going to neglect air resistance. If we neglect this air resistance, then the x, or the horizontal direction of motion, is pretty simple. In the x direction, the horizontal direction, horizontal, there is no acceleration. Okay, there's only acceleration in the y direction due to gravity. In the x direction, it's just simple constant velocity. So vx of t does not change with time. So if I make a plot of vx versus t, it's as simple and boring as possible. So something like this. Okay, just some constant like this. Now, if I were to plot the x position versus time, so x of t versus time, looks like, we can figure it out. If we have constant velocity, we should have a line whose slope is positive. Okay. And, well, where exactly it goes, I mean, the slope is determined by Vx, but where this is drawn up here or there is really determined by what the initial position is. So let's not worry too much about this. So this will be a straight line. The slope is just Vx, which is constant. Okay, if you have any questions, please ask the student who's supervising the lecture today. Okay, so as I said, the x motion is simple. Ax is equal to 0. There's no acceleration in the x direction. The velocity is constant. And so, if we talk about the initial velocity in the x direction, so the 0 for the initial, x for the x component, and let's say Vx is the final x component of the velocity, then they are both equal to each other and equal to some constant value. Alright, so if I have constant motion in just the x direction, the kinematic equations, how things behave as a function of time, kinematic equations in the x direction are the ones we know for constant velocity, so there's no acceleration. The final velocity equals the initial velocity is equal to the average velocity. Okay, they're all the same, it's just a constant. And so if I want to know how far does something go, if I know the initial velocity, that's the same thing as the average velocity, so then I can just take v0x and multiply it by delta t, and that will give me the displacement. So it's very simple. This is just constant velocity. Okay, so constant velocity in the x direction. Now in the y direction, things are more complicated. In the y direction, we have gravity on the surface of the Earth, producing a downward acceleration. We said the AY is negative 9.8 meters per second squared. Remember, we're taking positive y to be in the opposite direction, so gravity points down. Right, so remember that's just minus what we call minus g. So, if we plot the plot of the y component of the velocity versus time, this will be a straight line because we have an acceleration. The acceleration will give me the slope of the velocity versus time. So the plot of Vy versus time is a straight line with slope minus 9.8 meters per second squared. Okay. So generally it looks something like this. Vy go like this. The slope equals minus 9.8 meters per second squared. Okay, so that's what the velocity looks like. So let's just, I didn't tell you anything about the initial velocity. Let's say t equals 0 is positive, and then eventually it becomes negative. Then if I plot the corresponding plot of y of t, position in the y direction versus time t, is going to look something like this. Okay. It has, over here, the y is positive, so it has the slope up, but at this point the y component of the velocity goes to 0, so it will have a flat top where the slope is 0, and then it will have a slope that's negative. Okay, so remember the value of Vy gives me the slope of the y position at that time. And so it's going to look something like this. Okay, some downward parabola, or upside down parabola. Okay, if you have any questions, once again, please ask the student supervisor today's lecture. Because we have constant acceleration, the kinematic equations are the ones we've already been studying for constant acceleration, the kinematic equations. For the y direction are, okay, AY is negative 9.8 meters per second squared. And I'll just write down all the formulas we learned. So the final velocity is equal to the initial velocity, we're all doing the y direction, plus the acceleration in the y direction times delta t. The change, the displacement, the change in the y position is equal to 1/2, or the average of the y final, the initial. Okay, this is the average of the initial, or the final and initial, times delta t. We had another formula that the average velocity, we derived this as well, was 1/2 Vy plus V0y. Okay, so this was not all that useful, but the ones that were really useful were this one, as well as this one, y minus y0 is equal to 1/2 ay delta t squared plus initial velocity v0y delta t. And then we had the formula without any delta t's. We had vy squared, v final squared minus v initial squared is equal to 2ay y minus y0. Okay, this is exactly the formulas that we've studied before. The only difference maybe is you see these y's explicitly appearing to remind us we're talking about the motion in the y direction only. Now, note that since x of t versus time t is a linear plot, linear or straight line plot, when we plot y versus, instead of t, but versus x, we also get an upside down parabola. Okay. All right. Now I've told you. Well, let me make a plot. I'll just say it, make a plot. So if I have y versus x, it also looks like this parabola, upside down parabola. Okay, so I told you in the x direction we have constant velocity, in the y direction we have constant acceleration. Let's talk about the strategy how to solve projectile motion problems, because these can get a bit complicated. But if you know the basic strategy, you can solve all these problems. So let me first tell you the key points. So one key point is the fact that you treat the x motion, the x direction motion, the x motion, or just say x motion equations, and the y motion equations independently, separately or independently. You do each one separately. Now, there's another point to this strategy that I should mention is that the only thing linking the two sets of equations, meaning the x and the y equations, is that the elapsed time, delta t, is the same for both. Okay, there's obviously feeling the same time. Okay, so if you don't know delta t, the first goal is to find delta t. Okay, so now that's the general strategy. Let me now go through sort of a cookbook recipe of how I think about solving these projectile problems. Okay, so here are the suggested steps. Step 1. Take the information given about the initial velocity, if any is given. Sorry, initial velocity, if any is given, and use trigonometry to get the x and y components. Which we'll call v0x and v0y. Okay, that's really a good thing to do. Very often this will be the very first step you do. You're given some initial velocity, you're maybe given some angle, something or another, and so now what you can do is you can get the v0x, okay, this guy here, and then you can get the v0y. Alright, so if I take this to be positive x and this to be positive y, so this is up and this is horizontal, then v0x will be obviously the adjacent side, so we have v0, the magnitude of v0, cosine theta. If we use the shorthand for v0 without the vector hat is the magnitude, then just write v0 cosine theta. And then v0y will be the magnitude times the sine of theta, or just plain v0 times the sine of theta. Okay, now step 2. So step 1 was to get the initial velocity components. Step 2 is choose to work with either the x direction or y direction based upon which direction determines the thing you want, which is the first thing you want, which is delta t. Okay? Maybe this is not really clear how I know which determines delta t, but let me just give you some examples. Okay, so if the final point is when the object reaches a certain height, example, it hits the ground, that's clearly a certain height, or Another example would be when it reaches the top, where it's at its turning point for the y direction. Then, in this case, you start with the, try to guess what I'm about to say, then you start with the y direction, the y motion. Okay? Why is that? Because if the final point, when the clock stops, is when the object reaches a certain height, that's all determined by the y direction motion, the constant acceleration in the y direction. The x direction really does not affect how high it will go up or go down. Okay, it's completely independent. But if you have, let's say, so I have to admit, many of the problems are like this. The stopping time is when it hits the ground or when it hits the top, something like that. But you may have another problem, another kind of a problem, if the final point is when you reach a certain horizontal distance, and let me give you an example. One example would be hitting a vertical wall. Okay, at that point you stop the clock when it hits the vertical wall. Then, in this case, how far it goes horizontally, that determines the final time. Then you start with the x motion. Okay? In either case, whether you start with the x or you start with the y, solve the kinematic equations and determine delta t. Okay. Now, step 3. We assume we have delta t. Now we use delta t and the kinematic equations for the other direction. To solve for the unknowns you want. Of course, we're going to do some examples, but just to review, step 1 was to take the information about the initial velocity, get the x and the y components using trigonometry. Step 2 is to figure out which direction determines the delta t when the final point is reached. If it's determined by how high you are, or whether you reach the ground or hit the highest point, then it will be the y direction that you start with. If the final point is determined by how far you've gone horizontally, for example, hitting a vertical wall, then you start with the x motion. Okay. So then you solve the kinematic equation, you determine delta t. Now step 3, use delta t and the kinematic equations for the other direction to solve for the unknowns you want. Alright, so these 3 steps are sufficient to solve just about any problem we'll be doing in class. You can cook up a more complicated problem where these steps aren't enough, but these steps will cover pretty much everything we need for this class. Okay, let's do an example. Let's say a football is kicked at ground level with speed 18.0 meters per second at angle 32 degrees, 32.0 degrees to horizontal. That's the angle it makes with horizontal. Clearly it's above horizontal because the ground won't allow it to go below horizontal. And the question is, how much later does it hit the ground? And the other question you might ask is how far does it travel horizontally? I didn't say horizontally in the notes, but that's what I meant. Okay, so before we go over the solution, I'm going to turn off the video and let you think about that to give it a shot yourself before we go over the solution.